Good morning, good afternoon, good evening. This is Mr. Payne bringing you other types of linear regression. Unit 10, Lesson 8. Objective today, you will be able to decipher between exponential, linear, and quadratic lines of best fit. You will also be able to use your calculator to identify the exponential regression equation. In the last two lessons, we fit bivariate data sets with lines of best fit. Sometimes, though, linear models are not the best choice. We can fit data with all sorts of curves, the most common of which is linear, exponential, and quadratic. These words are not new to you. But there are many other types. Before we look at exponential and quadratic regression, recall the general shapes of these two types of functions. Don't forget, this is exponential, this is quadratic. Quadratic, you're going to have it come down, it's going to get to a certain point and then start coming back up. That's what deciphers the difference between quadratic and exponential. Let's practice real quick. A, if you notice, it's exponential. B, quadratic. C, exponential. D, linear. E, linear. And F, quadratic. Pretty easy, self-explanatory. We're going to move on now to talking about exponential regression formula. Our calculators can produce equations for exponential of best fit and quadratic of best fit, along with a lot of other types of curves. Today we're just going to focus on exponential of best fit. Biologists are modeling the number of flu cases as it spreads around the particular city. The total number of cases, Y, was recorded each day, X, after the total first reached 16. The data for the first week is shown in the below table. Use your calculator to find the exponential regression equation. So the first thing we're going to do is type this data into our two lists, remembering that my X is going to go into L1 and my Y's are going to go into L2. Once I have both of those pieces of information in, I'm going to hit Stat, Calc, 0. And 0 is going to give me EXP, so my exponential regression. Once I have that, you can see right in my calculator, it's my A and my B again. So my A equals, and we want to round everything to the nearest hundredth, is 15.92. And my B is 1.12. If I want to put it properly into my formula, it's Y equals A 15.92 times 1.12 raised to the X power. Based on the regression equation, how many total cases of flu will be there after 2 weeks? Well, one of the key parts there is understanding 2 weeks. 2 weeks is equivalent to 14 days. So I want to plug into my calculator Y equals 15.92 times 1.12 raised to the 14th power. And if I solve that, you'll be able to, if you type that into your calculator, you'll be able to get the correct answer of, and I'm looking for it right now, I apologize, 78 flu cases. According to your model, by what percent are the flu cases increasing on a daily basis? So I want to look at whatever my slope is, or whatever my increasing, my B. So what is it changing by? It's changing by 1.12. If you remember when we talked about exponential, it's really, when I separate it, it's 1 plus 0.12. So it's increasing above that 1 12%. D. Hospital officials will declare an emergency when the total number of cases exceeds 200. On what day will they need to declare this an emergency? Well, here's what you do. Did you notice that this equation starts with y equals right here? I would like you to hit y equals on your graph. Remember that y equals is up in the top left-hand corner. And type that into y equals 15.92 parentheses 1.12 caret x. When you get that, let's go to our table. I want us to go to our table and identify where my 200 mark is. Well, my 200 mark is right in this area, right in here, between 22 and 23. If there's 22 cases, or if there's 192.64 cases on the day 22, do I have to tell anybody? No. But as soon as we get to 215.75 cases on day 23, that's when I have to call somebody. So day 23 is when I'm going to have to call somebody. So do you notice how I have to use my entire calculator, things from new and old, in order to answer these questions? So really, regression, as mysterious as it may be, is all about finding the best version of whatever curve we think fits the data best. The cost per widget, let's look at exercise 3 to prove that point. The cost per widget produced by a factory generally drops as more are produced, but then starts to rise again due to overtime costs and wear on the equipment. Quality control engineers recorded data on the cost per widget compared to the number of widgets produced. Their data is shown below. Remember, when I input this data, my x's are going to go into line 1, my y's are going to go into line 2. Why should a quadratic model be considered for this data set as opposed to a linear or exponential? Well, let's take a look at my y values. Notice my y values start high, they go low, they start going lower, they start going lower, then all of a sudden they turn and they start going back up. So right in this area right here, there was some type of turning point. Let's observe that in question B. So A just answered that. The outputs decrease, then increase. So to see if they're going down, they're going down, they're going down, they're going down, turning point, now they're going up, up, up. And let's view that in my calculator. It says use your calculator to create a scatter plot of this data to verify the quadratic nature. If you notice, there it is there. That looks like a quadratic because it's going back up. It's not exponential. An exponential would be way down here and can make a slow gain up. This is definitely coming down and going back up. So therefore, it is quadratic.